I'd like you to start with this warm-up today. Press pause when you're ready for the answer. Press play again. Okay, so as you can see, we're expanding. So it would be log base 5 of 25 plus log base 5 of x squared. Notice the product minus log base 5 of the quantity y plus 1 cubed. Then log base 5 of 25 is 2. My exponent moves to the front, so it's 2 log base 5 of x. This exponent moves to the front, minus 3 log base 5 of y plus 1. In the second example, I'm condensing. So I have a sum here and a difference here. The first thing that I do is I move the coefficients up to exponents. So this 2 moves onto the x minus 1 as the exponent. The negative 3, or not the negative 3, 3 moves on to the y as an exponent. Then I have ln of x times x minus 1 squared, because this is a sum, and the y cubed goes to the denominator. Today we're going to solve exponential and logarithmic equations. So, some strategies for simple exponential equations. The very first thing you're going to do is you're going to rewrite both sides of the equation in terms of the same base, if you can. So my example over here says 2 to the x minus 3 equals 32. Luckily for us, we can write 32 as 2 to the 5th. The next thing I do is I equate the exponents. So I have the same bases on either side. So then I set my exponents equal, and I solve for the variable. I'd like you to try these. Press pause when you're ready for the answers. Press play. Okay, so here I could write 8 as 2 to the 3rd. Then I equated my exponents. X minus 1 equals 3, so x must be 4. Now in this example, I did it a little bit differently. I could have written 27 as 1/3 to the negative 3 power, but I think it's easier to see it as a power of 3. 27 is 3 to the 3rd power. I rewrote 1/3 to the y is 3 to the negative y. I just thought it was a little easier to see that way. Then I equated my exponents. Negative y must be 3, so y therefore must be negative 3. So now the next question is, what do I do when I can't write either side of my equation with the same base? So here's an example of that. The first thing you're going to do is you're going to isolate the exponential expression. So if you look at my example here, I have e to the 2x. I'm going to solve this equation for that. I do that by adding 2 to both sides and then dividing both sides by 3. Then I take the same logarithm of both sides, and I choose to do so with the same base. So since I have an e to the 2x, I use log base e, and another way to write that is ln. And I do that because they are inverse functions. So ln of e to the 2x equals ln of 3. And because they're inverse functions, I know that this undoes the exponent. So I end up with 2x equals ln of 3. And then I solve for the variable. X equals 1/2 ln of 3, or ln of 3 over 2. Okay, I'd like you to give these two a try. Press pause when you're ready for the answers. Press play again. So you can see on both sides of my equation, I already had the exponential part isolated, so I took log base 5 of both sides. Then that log base 5 undid 5 to the y squared, so I got my exponent out. And then I end up with y equals plus or minus, it should be the square root of log base 5 of 27. I don't know why I left that out. There we go. The square root of log base 5 of 27. In my next example, I solve, my 10 to the 2x minus 3 is already isolated. So then I took log base 10 of both sides. So you'll remember that log base 10 can be written as log with no base written. It's understood that that's log base 10. If I take log base 10 of both sides, I get my exponent out. That's equal to log of 7. Now I solve for x. I add 3 to both sides, and I divide by 2. Now, I'd like you to see one other way to solve these problems. So let's say we are solving 5 to the y squared equals 27. One other way to do this, as you get into upper level math, we primarily use log base e or log base 10, and more often than not log base e. You can solve this by taking the natural log of both sides, log base e, and then what ends up happening is this exponent, y squared, moves to the front. And then you divide both sides by ln of 5. And then you take the square root of both sides. And you will find, if you plug each of these into your calculator, that you get the exact same answer. So, again, we become more often than not using natural log of both sides. I could have done that here as well. You get the same value. You guys know how to solve that. Now I'm going to solve a different type of equation. There's no way to isolate 10 to the x. I've got to make a substitution so that I can solve for that. Now, notice 100 is 10 squared. Now, remember, when you have a power raised to a power, you can multiply those. And now I'm going to rearrange a little bit because multiplication is commutative. And if I make a substitution, I can rewrite this equation like this. Now I have a quadratic, and that's factorable, and you factor it. So that's a minus 2, a plus 1. So you get a equals 2, or a equals negative 1. But I was not looking for a. I was looking for x. 10 to the x equals 2, or 10 to the x equals negative 1. Now, if I take log base 10 of both sides, I find that x equals log of 2. And in this particular case, there is no power that I can raise 10 to get a negative value. Even if you don't see this, you can take log base 10 of both sides and get log of negative 1, which is undefined. There is only one answer to this equation, and it's log of 2. Okay, now sometimes you have to solve a logarithmic equation, and in this particular case, the first thing you're going to do is combine your logarithms on each side of the equation. You want to get log equals log. So on the left side, I condense. So this is log of x times x minus 3. Now I have log base 10 of x times x minus 3 equals log base 10 of 4. Now the next thing I can do is equate the arguments. So x times x minus 3 has to be 4. And then I solve my equation. So I distributed the x here. I factored, and I found that x equals negative 1 or x equals 4. Now, in this case, you can get what you call extraneous solutions. The reason that happens is you have a restricted domain on the logs. You cannot have negative arguments. The arguments must be greater than 0. So when you plug in -1 here, I'd end up with log of -4, and that's just not possible. So it cannot be -1. But if I plug in 4, I get a positive argument here, here, and here. So life is good. I've eliminated one extraneous answer, and my solution is 4. Now, I'd like you to try this one. Press pause on your video. When you're ready for the answer, press play again. So, again, we condensed our logs. So I had ln of x times x plus 3. I equated my arguments, and then I solved for x. I distributed my x. I set it equal to 0. I factored, and I determined that -4 was extraneous. I ended up with a positive argument here. That was fine, but then I had a negative argument there. That's not okay. With the 2, I had a positive argument, positive argument, positive argument. Life is good. Now, I sometimes need strategies for solving logarithmic equations when I cannot get a situation where it says log equals log. In this case, we still combine and isolate the logarithmic expression. So on my left side, I had a difference of logs. The difference of the logs is the log of the quotient. So I have log base 5, I didn't write that in, log base 5 of x plus 2 over x equals 2. Now, remember, the inverse function of log base 5 is the exponential 5 to the x. So what I did was I raised both sides to the power of the log base. So if you can imagine, I made each of these my exponent on a base of 5. So I have 5 to the log base 5 of x plus 2 over x and 5 squared. These are inverse functions. That gets my argument out, and I end up with x plus 2 over x equals 5 squared. Then I solve for the variable. So I multiplied both sides by x, and then I solved by subtracting x from both sides. That gave me 24x equals 2, and dividing both sides by 24. So I ended up with 1/12. And again, you need to double check to make sure your arguments are still positive, which they are. So my solution is x equals 1/12. I'd like you to try to solve this. When you're ready for the answer, press pause, and when you're ready for the answer, press play again. Here is my solution. So I combined my log on the left-hand side, so I had the log of the quotient. This is a difference. The difference of the logs is the log of the quotient. I raised both sides with a base of 3, made both of these my exponents on a base of 3. So I got 9x over x minus 8 equals 3 to the 4th, which is 81. And then I solved, and I ended up with x equals 9, and I made sure that my arguments remained positive. Now, this one looks hard, but it's really not as hard as it looks. So I have ln of log base 10 of x. Well, the base on ln is e, so I'm going to make each of these my exponents on a base of e. When I do that, I get log base 10 of x out. E to the 0 is 1. Now I have base 10. I'm going to make each of these my exponents on a base of 10. And I find that x is 10. This one looks a little bit different. We're going to have to use some properties of exponents to help us out. My problem is it would be very nice if this was 5 to the power log base 5 of x, because the this being in my exponent, my log base 5 and my base of 5 would cancel. but it's not quite there yet. So using the properties of exponents, I can rewrite this like this. Now I'm in a good place because that's going to cancel. And I end up with 25. The x comes out. That's equal x cubed. Now I can solve for x by setting this equal to 0. 0 equals x cubed minus 25x. I'm going to factor that, factor out an x. Now x squared minus 25 factors. So I end up with x equals 0, 5, or negative 5. But I've got to make sure that this makes sense. If I look at 0, I cannot have a 0 as an argument in a log. It's undefined. There's no way that 5 raised to any power will be 0. So that one will not work. If I look at positive 5, that is absolutely okay. Positive 5 is okay. So this one is a solution. If I put negative 5 into my log as an argument, that won't work either. So that one is also extraneous. There's one solution to this equation. That concludes the lesson for today. Take a look online and work on your assignment.